Welcome everybody to this conference on the economics of climate change on behalf of myself, Francesco Caselli, and the other organizer, Alexander Ludwig, Loriana Perizzon, Rick van der Pleug, and Tobias Ströger, and the sponsoring organizations, which are CEPR, the Macroeconomics and Growth Program, Foundation for Law and Finance, and Goethe Universität. And with that, we can start. The first speaker is Thomas Hickler, and the paper is Climate Change and its Impacts on Biodiversity, Ecosystems, and Society.
Yeah, thanks for the introduction. I'm very much looking forward to this workshop because I believe that we really need more integration of natural science and economics thinking to achieve the transformations which will be necessary to leave this planet in a state that our children will still like. I will start first with some general things about the climate system, which are important, I think, to understand how we can work with climate scenarios and scenarios of impacts of climate change, also in economic assessments. So regarding some basics, first of all, I want to emphasize that the potential changes we talk about are really massive. What you have normally seen, I guess all of you know the IPCC figures for the last 100 years. You should also see my cursor. Do you see my cursor? I guess so, huh? Yeah. So the IPCC figure over the last 100 years, 1 degree warming, and then the future scenarios with the different representative concentration pathways until the year 2100. But of course, the world doesn't end in the year 2100. This goes actually on in the future. And we see here the blue future, which is the most optimistic representative concentration pathways in terms of our emissions, where we would actually reach the Paris 2-degree goal if we consider the average of all climate models. But of course, there's uncertainty. So what is shown here, the lines, is the average of all climate models under one concentration scenario of greenhouse gases, and then 2 standard deviations. What I want to illustrate with this very fundamental figure is how big these changes really are, because maybe sometimes people think 3 degrees warmer than Frankfurt, that's Florence in Italy, not a terrible place. And maybe 4 degrees doesn't sound very much either, but we should keep in mind when the world the last time was about 5 degrees colder than today, this was an ice age. And when the ice age was the coldest, London and Berlin were under ice. In Frankfurt, we were a bit more lucky. We lived in a mammoth steppe here, close to the ice. Now, if you now look into the future, even if we only have 1 or 2 degrees additional warming, we are already back in the Pliocene, like 2.5 million years ago. That's a world without the big changes of ice ages and warm periods that we have seen over the last, in particular, 1 million years ago. And if we push it really hard and we take the risk of strong climate warming, like 4 or 5 degrees global average temperature, you might actually even end up in an area called the Eocene with like subtropical vegetation in northern Canada and much warmer poles. So very, very big changes if we really take the risk. Now, looking back again to the Pliocene 2.5 million years ago, which was, as you see here, 0.8 to 2 degrees warmer compared to pre-industrial temperatures. These are estimates. Oh no, this is the last interglacial, the 0.8 to 2 degrees. The Pliocene is here 0.8 to 3.6 degrees warmer than pre-industrial temperatures. Already in the last interglacial, sea level was 6 to 9 meters higher, with maybe 1.5 degrees warming. And about 2.5 degrees warming produced sea levels of 10 to 30 meters higher than today. And now, luckily, the ice sheets are melting slowly. So this is the equilibrium response of sea level to climate change. But I think it's important that our decisions today will change the geography of the planet. These are long-term changes, and I think they don't get the attention they actually should. I'm also mentioning this because maybe some of you have read the sea level projections from the last IPCC report. The last IPCC report, the big one, projected as a maximum 1 meter sea level rise until 2100. This number is outdated by now. And if you look at this climate science special report from the US from 2017, here the authors say, yeah, standard models maybe don't produce more than a meter, but we cannot outrule the possibility of nearly up to 2 meters or even a bit more until only 2100. And I think such updates, they have to be considered in assessment of the economic impacts. And my impression, without knowing the economy models very well, is that the economic impact assessment part sometimes lags behind the biophysical state of the art. And these lags are really unnecessary if we talk to each other. So sea level is one example where the latest projections have become more negative, and surely with very big impacts in large parts of the world. Just an example, in Bangladesh, if coastal protections are not reinforced, already 1 meter would force like 40 million people on the move.
Thomas, can I just jump in a clarification?
Yeah.
You're talking about this is a massive change from 1 meter to the number you're showing that. What is the new information that has come in that has caused us to go from 1 meter to 10 to 30?
It's partly new models which simulate dynamic ice collapse better than before. So the ice sheet is not just a big homogeneous cake anymore that melts. It's a better understanding of how the glaciers flow over, Greenland or Antarctica. And it's also new results from changes like paleo changes in the past in climate and sea level. And if you look at this climate science special report, which is also written for decision makers, there's a nice summary about these numbers. But generally, how fast sea level will rise is something that is very uncertain, unfortunately. So it's not possible really to nail down exactly how much it will be. But the latest discussion in the literature is more negative than what's in the last IPCC. The IPCC is, by the way, the big reports are updated right now. So they will come out soon. And then it's always good news for some time. The most up-to-date information is nicely summarized in these reports. Now, just regarding the ice sheets, this is now illustrated here with the Greenland ice melting, which can be reconstructed with satellite techniques, where you see where the melting can be better and better quantified. And I'm mentioning Greenland here because Greenland is one example where climate scientists talk about the so-called tipping point, meaning that once it starts melting, you cannot turn it back. And the reason is that as Greenland melts and the surface becomes lower, it also becomes warmer. It's the same effect if you climb up in a mountain, it gets colder if you get higher in elevation. So if the elevation declines, there's a positive feedback on the melting. And this is why there's a debate if maybe climate is already beyond the point of return. Now the question is, will it take 1,000 years, 2,000 years? Hard to say. So much about sea level. Now about some other fundamental things. Now this is again the figure I guess you all know. This was also in the figure I showed in the beginning. The last 100 years, 1 degree warming, and then the future with different representative concentration pathways. And actually with this optimistic one, on average over all climate models, we reach at least the 2-degree Paris goal. So now just to remind us what's necessary to get there, as CO2 does not react in the atmosphere, it basically stays there until it's taken up by the ocean. In order to achieve this future, we have to get to net zero emissions by about 2070. Then we have to take up a few billion tons of CO2 from the atmosphere each year, for example, with carbon capture and storage techniques. So this future, oops, sorry, this future here, the most optimistic one, might be technically feasible, but it's very, very optimistic. Most of the literature is more discussing that we seem to be on the red one here, which means continuing CO2 emissions, increasing CO2 emissions over the whole century. So a strong increase. To be honest, I think the red future here is not realistic. Partly because the impacts would be too strong, and the other reason is, I mean, to put it in simple words, you won't be so stupid. Renewables are already cheap enough. However, this future here is probably also very, very unrealistic, because the necessary transformations of our energy systems and so on, I mean, they're very, very massive. And if you just look at current investments in, for example, coal-fired plants, we're not going to make it. I mean, you don't build new power plants and dismantle them after like 2-3 years or so.
So just to understand, the purple path down at the bottom is what you would need to get the purple path at the top.
Yeah, the blue one, I'd say. Yeah, the blue one exactly would get this one at the top, and the red one would be the top one here. And the two in the middle are not shown in the top for simplicity. And the warmest one, you know, the most negative one from a human perspective, has an average warming here of like 4 degrees. But I mean, there's a big range. There's a big uncertainty in the climate system. And it goes up to nearly 5.5 here. However, the newest generation of climate models, they have a so-called higher climate sensitivity. They are more sensitive to increasing CO2 levels. So it seems like the new upcoming IPCC report will actually get higher here. But we have to see how it will look like. We will know in a few months. Now, another fundamental thing about the climate system is that it has been very, very dynamic already in the past. We see here from ice cores from Antarctica, the last 11,000 years, stable climate and temperature. We see, you know, the ice age, which was pretty dynamic, the last interglacial ice age, and so on. And here the associated CO2 concentration. So I just want to shortly illustrate what happens here if we leave an ice age and go into a warm period. This is driven by how Earth is rotating around the sun. There are some variations, for example, in the tilt of the Earth axis, which actually makes a difference between summer and winter. And there are some other variations. I'm not going into the details now, but what happens here is if there is more solar radiation hitting the far north of the Earth in summer. For example, when the axis is more tilted and the sun is here and there's more tilt in the axis, the summers get warmer. Then ice and snow is melting. The Earth gets darker, it absorbs more temperature. So as the Earth becomes darker and absorbs more temperature, the ocean starts outgassing CO2. And we also get more water vapor in the atmosphere because we get more evaporation of water from the ocean surface. So water vapor is the most important greenhouse gas. CO2 is a greenhouse gas. We also get more methane emissions from wetlands as the Earth becomes warmer and wetter. And to cut a long story short, we have a trigger here, how much solar radiation hits the far north of the Earth. And then we get many, many feedbacks leading to very rapid climate change. And this is why it's also so difficult to predict not the direct effect of CO2 in the climate system, but all these feedbacks. You know, how much more water vapor will be evaporated? How will the ice melt exactly? How much more methane will be produced, and so on. So now one conclusion from this figure is what some might say, okay, the climate system already is so dynamic without humans, what can we do to it? Another more reasonable interpretation, I think, is that the climate system for 11,000 years now, where our civilization evolved, has been like a sleeping bear. And now we irritate the bear with a sharp knife. Yeah. And we hope that he's not waking up, kicking in some feedback mechanisms which he might not be able to stop. So now which aspects of the character of the bear might make some problems to us? One obvious one is on the melting of the permafrost. The permafrost around the globe stores a lot of carbon. It's nearly double as much as the carbon as CO2 and methane in the atmosphere. And this is just one site of many permafrost sites around the world where the permafrost has started to melt. And the permafrost feedback, like the additional CO2 and methane put into the atmosphere, is not even included in many climate models yet. It's starting to come to be included in more climate models. It's going to be a positive feedback on climate warming. How strong it will be is still debated because the model projections are very different. And yeah, I have a reference here if you want to look more into the details. So now a summary of these tipping points in the climate system without going into all of them. But there are a few which I already mentioned. I mentioned the Greenland ice, part of the ice sheet in West Antarctic. The West Antarctic region might also be unstable. There are concerns about coral reefs, which I guess you have all heard about. Here's the permafrost. And there are some others also related to the Amazon forest, for example. So one has to keep these climate tipping points in mind. It's not about we are facing like a continuous, slow but steady increase in warming. There can be rather rapid changes, but they're extremely hard to predict. So we are facing a system with very, very large uncertainty. And then we also have interactions, which right now are quite lucky for us, which is here illustrated as a breathing of the Earth, where we see when how the seasonality of vegetation also drives the seasonality in the CO2 concentration. But even concerning our total annual emissions, land ecosystems and the ocean currently take up about half of our CO2 emissions. Climate warming would be much stronger if this would not happen. But of course, the question is, will this also continue in the future? And this is highly uncertain, in particular when it comes to land ecosystems, where the uptake of CO2 is quite variable. In some years, it's nearly half of our emissions by land ecosystems, and in other years, it's much, much smaller. And this is also why, by the way, there's a lot of talking about reforestation to combat climate change, to mitigate climate change. There is indeed a potential to take away CO2 from the atmosphere, for example, with reforestation. But it's pretty minor compared to our current emission levels. So now I'm coming to more to the impacts of all this. I guess most of you are familiar with this figure. These are the economic impacts quantified by reinsurance companies. The number for 2020 is 210 billion. But I'm now talking a bit more about the biophysical basics of this. Now, this is again the picture I have shown from the Taunus Mountains. You can see, actually, if you look closely, you should be able to see Frankfurt down there, which we couldn't before, because since the very dry summer of 2018, we had massive forest mortality in large parts of Central Europe. The Norway spruce trees have been hit very hard, but even like the native beech forest is suffering substantially. And if we now put this summer in a perspective, 2003 we had a similar summer. It was actually even hotter, but the dryness was not so long. 2003 is also the summer which you might know from the news, because there are estimates that about 70,000 people in Europe died from extreme heat. And this excess mortality is sometimes now compared to the excess mortality from COVID-19. However, if we look at the 2003 summer and we compare this with the strong climate warming scenarios, here different realizations of a model for Southern Europe, we see that 2003 by 2040 or 50 could be normal. And the same applies to 2018. And that, of course, also means that we might face even hotter and even drier summers. And this is a challenge for natural ecosystems, not so much in agriculture, because I can change my crop from year to year, but in forests, of course, where trees get 100 or 200 years old, it's a real challenge for forestry to cope with this rapid change and with the uncertainty. Now, this is a projection of how the forest cover across Europe might change if the relationship between climate and tree species stays the same, but then assuming a climate change scenario, an intermediate one, not a very strong one. So this is a statistical model, and here you see the forest plot network, which has been used to make the model. What we see here, all this brown stuff here in this projection is basically Mediterranean oak forest, including evergreen Mediterranean oaks like stony oak, Quercus ilex. This may not sound so badly, but if you look at the economic revenues from these forests, the damages here, the estimated damages, they go up to several $100 billion across Europe. So they are very fundamental, but this is only like the forestry damage, you know, like the money basically you make with the timber. It ignores many of the ecosystem services provided by forests, such as you get cleaner water under forests, you get more groundwater recharge. Of course, we have the recreational value and so on. So now agriculture, very important topic, of course. What about crop yields? And what we see here, this is an average from many different global climate models and crop models. We see a general trend towards lower yields in the hot tropics, in particular here for wheat, but potentially higher yields, of course, in the north where it's cold. So there are, in cold areas, there can also be positive effects of climate change, for example, on our crop yields. So now for crop yields, of course, it's also important to look at the redistribution of precipitation and water resources globally. Here I just want to illustrate the difference between the temperature projections at the top, where these little small points basically mean all climate models make the same, high certainty. This precipitation, you see few areas with points. You see many areas where with lines maybe, or there's no special pattern, meaning that climate models don't agree, meaning much larger uncertainty. But there is nevertheless a trend, what's rather robust, that we get less precipitation like in southwestern Africa, much less in Europe, in southern Europe. This is very robust. If we look into more regional projections, this is unfortunately very robust, that in particular southwestern Europe will be hit hard. And the same also applies for here southwestern North America. Now, another issue with water is not only that we redistribute water resources, it's also that the glaciers melt, like here the Himalayan. And glaciers are for agriculture are like a dream, because the whole summer you have a little melting from the mountains. So you have very, very predictable water supply. When the glaciers are gone, of course, you get the water when it rains, and otherwise you don't have water. And now what I've not talked so much about so far, which is very important, that we get a better and better understanding not of average changes, which are not very, may not have very dramatic impacts because we can adapt to them. This is now a recent compilation of changes in extreme events, combining climate models with state-of-the-art sectoral climate impact models, crop models, wildfire models, where I have been involved here, one tropical cyclone model, hydrology models for river flood, and of course heat wave models. And what you see here is, for example, let's look at river floods. If we have a 2-degree warming, on average across all models, we get 3.1 times more extremes. And this is now a global area and the global population exposed to the extremes. So it gets, unfortunately, more and more robust, the finding that we have an increase in extreme events with climate warming. And the increase so far is a doubling. So this study actually started at pre-industrial levels. And even if we hit the Paris 2-degree goal, a 5-fold increase. And these extremes are going to are going to give us trouble. And what I've seen so far in economic impact assessments is basically very simple models of the plant productivity, sometimes where the productivity of plants or crops increases when it gets warmer and wetter. But things like this have, to my knowledge, not been accounted for very much in economic impact assessments. And yeah, the science is out, so it's just waiting there to be used. So now about biodiversity. I thought today, for the sake of time, I speak mainly about indirect effects because they will be the strongest, at least in the shorter term. And by the way, I'm touching among many different things here without going into details. So please feel free to pester me after the talk, for more details about anything I'm saying now. For biodiversity loss, which is dramatic, but climate change is not the main driver so far. And it's not going to be with 1 degree warming either. The main driver for biodiversity loss is very clearly land use change on land and direct exploitation, fishing basically in the oceans. And I want to illustrate this here. This is forest clearance in the Amazon region. It's mainly done by fire. These fires in the Amazon are partly driven by climate change when we have a big drought, but they're much more driven by political decisions. And of course, if you burn tropical rainforest, you kill many species, you decrease biodiversity, and you also emit a lot of CO2 to the atmosphere, by the way. So here you see an estimate that 20 billion tons of CO2 have been emitted by deforestation in the Amazon since over the last 20 years. So basically, on average, each year, 1 billion tons of CO2 is emitted from the atmosphere, from the Amazon by deforestation. And you can compare this 1 billion ton by the emissions of Germany, which is 800 million tons. So this is very substantial. If you want to do something about climate change and biodiversity loss, stopping deforestation is the most effective one. And that would have a big impact. And that, of course, also means living other livelihoods also on our side of the planet, because as described here in the global IPBES report, the deforestation in the Amazon is mainly driven by meat consumption. Grazing lands for animals, or fodder for our meat industry here in Europe. So meat consumption is a big factor here. And by the way, in case you're not familiar with IPBES, the citation here is from the Global IPBES report 2019. IPBES stands for the Intergovernmental Science Policy Platform on Biodiversity and Ecosystem Services. So it's basically the IPCC report for biodiversity and ecosystem services. And in this report, I've also been involved in one chapter. So for biodiversity loss, land use change is very important. And that also implies, by the way, that climate change can have indirect impacts on, very important indirect impacts on biodiversity, which are driven by our decisions about bioenergy. I don't know how many of you know that if you tank your car with diesel gasoline, there's some palm oil included normally. So palm oil in diesel means tropical forest is burned, replaced with palm oil plantations, and then we put it into the tank. It is, of course, totally ridiculous with massive CO2 emissions, but this is happening. So bioenergy is a response to climate change to mitigate it, but it has sometimes become a threat to biodiversity. Which is why these ideas to deploy like large-scale bioenergy systems, millions of hectares with bioenergy plants, which you can burn or you can make biogas, natural gas. You can also produce gas from the plant residues. And the CO2 that's produced, you can put back into the ground, carbon capture and storage, like the Norwegians have done it with their oil platforms for a long time. This has been promoted a lot to remove CO2 from the atmosphere because the biomass is always growing again. It's regrowing again. food. We live in an age of a biodiversity crisis. If we now also start to have massive bioenergy plantations to take out CO2 of the atmosphere, we have to think very carefully about the side effects. So that's an indirect effect on biodiversity from our reaction to climate change. So now I come to my last point, which I think is very hard to quantify in models. And this is a big question: under which conditions can climate change increase the risk of armed conflict? It's a very controversial field of research. It has been debated a lot in connection to the conflict in Syria, which of course is terrible for the people down there, but which also has driven many people to become refugees. And you all know what these refugees, what this crisis has done with Europe, you know, the rise of the right, crisis of the European Union, very, very massive effects also far away. And I think that makes very clear that it doesn't make much sense in terms of climate impacts to just look at, you know, how are our forests affected? Or like in the UK and Germany, by the way, flooding is a big issue. But these, you know, indirect effects from far away, they, in my opinion, they can be much more serious, even for us, on top of the suffering of the people down there. If we look at the drought data here, the big droughts are here in brown or here in red. Of course, one also has to consider that the population has increased substantially. And this is something we see in general in the dry belt of the world. We have the highest population growth rates. We have low adaptive capacity. Yeah, we don't have a very good combination to cope with climate change. So this is now one example from an old study. And there are newer studies like the one by Schleusner down here, which I cite. Like a very simple summary of where climate might become a security risk. This is from the German Advisory Council to the German government. I'm sure the UK government has similar reports. And this is something where, you know, in the end, yeah, maybe the biggest threat is not the climate system, but humans. But it's a very, very controversial field of research. There's even a big debate between researchers working more with qualitative methods, which are very critical of quantitative analysis, where people, you know, simply correlate climate impacts, for example, with the number of conflicts. But yeah, I just wanted to mention it as an unresolved field, and surely as something which I think if one is thinking about the economic impacts of climate change, even if we cannot model this, even if we cannot quantify it, we should not simply forget about it. Okay, I think my time is out. I had a few, and I leave it here as it is, and I'm looking forward to your questions and comments.
Yeah, thank you, Thomas, for causing us nightmares for the next several weeks.
That was not my intention.
Okay, let me invite questions. Again, I remind you, if you are an attendee, I don't think you can just unmute yourself, but I think I should have the ability to allow, yeah, I can unmute you. So if you raise your hand, yeah, there we are. Okay, yeah, any questions, any questions or comments from anyone who is listening? Again, if you click on the blue hand.
Can I ask a first question to Thomas? Thank you very, very much for a very wide overview. Can you say a little bit more about the observed fact that the poles seem to be warming much more rapidly than the equator, and what's your view on that? And
I mean, this is very robust. This is also known from the past, that when the world was much warmer, you know, the difference in the tropics maybe was only 2 degrees, and at the poles it was 15 degrees. And there are good physical reasons why this is happening. I mean, part of it is the melting ice and snow. So the surface of the Earth in the far north becomes darker. It's a very simple physical effect, like the disappearing sea ice. And that's a positive feedback on climate warming. There are other reasons, like I mentioned, in a warmer world, we get more evaporation from water, from the ocean. So we get more cloud cover. And in the high north, the clouds make the surface cool less during the night. A cloudy night, it's very simple. And then there are some other factors, but I think these are the main ones. There is one exception in a way, and this is that the Gulf Stream has also weakened, the big conveyor belt of heat in the ocean, which makes our part of the world livable. I mean, latitude-wise, we are in Canada here, but luckily it's quite much warmer. But this conveyor belt has weakened over the last at least 30, maybe 40, 50 years, which is why if you look at global temperature maps, like a bit south of Iceland, we don't see any warming. So there are other things which complicates the story. Yeah, but this the so-called polar amplification, this is clear from the data, from the physical concepts. There's no debate about this. This is not very uncertain. Maybe if nobody's talking right now, I just want to mention regarding the nightmares mentioned. I think there are also very positive indications in terms of investments in global energy, like on a massive rise, even globally, technological developments. I mean, I haven't touched upon these, and others, to be honest, know more about it than I do. But I see also many positive signs that we can limit the problem. I mean, we have the technology, and maybe it doesn't even cost so much. And if we account the cost of letting climate change happening, I mean, it's clear that it's good business to minimize the risk of extreme climate change.
I mean, on that, Thomas, can I ask you? Sometimes there is a view which maybe is an excuse that someone uses, which is that because of the global nature. Actually, and this kind of gives a little bit into the next talk, kind of introduces a little bit the next talk as well, but it would be good to have your perspective. There is sometimes this view that unless all of the major economies in the world act in concert, basically there is no hope. I mean, I'm putting it too stark maybe, but you need to unite with everybody. US, China, Japan, Brazil, everybody needs EU, obviously. Yeah. I mean, is that how much truth is there in that?
Yeah.
You have a view on that?
Yeah, I mean, we clearly need everybody on board. I mean, clearly, if China and the US don't act, I mean, they stand for a large part of the emissions. And even, poorer countries in the south, like Indonesia and Brazil, if they don't stop deforestation, we cannot limit climate change either. So I would agree that everybody has to work together. But most of all, I would argue that it's a myth that it must be a contradiction between economic development and mitigating climate change. One could even argue that, I mean, we have technology now to reproduce energy in a sustainable way. And sometimes we are still locked into old systems where, to my understanding, even economists say like, they're too expensive. I mean, if you calculate the price of coal, for example, there are many studies on this, and I guess Ottmar Edenhofer will talk about this tomorrow. The pure economic cost of the emission of 1 ton of CO2 from coal-fired plants globally is like 190 euros. This is a massive externality. And I mean, things like this in theory or ideally would be included in our prices, and the whole economy would be more effective.
But Thomas, given those given those externalities, isn't there more that developed countries could do, for example, to stop the deforestation in the Amazon and give more support to people there, given that they are bearing the cost in some sense?
Yeah, I think definitely we could do more. Of course, in terms of doing more, it's a bit tricky. I mean, if governments like, you know, from the Germany or UK tell like a president in Brazil, stop deforestation. Yeah, people have tried with limited effects. And at the same time, as long as we subsidize, you know, our meat production halls, which depend on imported fodder from areas like the Amazon, I mean, it's hard to, yeah, it's hard to regulate something top down if you don't go for the driver in the underlying economy as well.
Thomas, let me ask you on that. On the issue of the driver. The UN is projecting a huge increase in global population.
Yeah,
2.5 Chinas over the next just over the next 80 years. You can imagine 2.5 Chinas to the world population. Do your projections take into account this population growth, or do we have like an extra really bad problem that we haven't discussed yet?
No, I have very good news about this. And may I even share, I have one backup slide about this. Can I share it? Yeah. The projections for our food production globally seem to indicate that our yields per hectare can increase more than the global population. And I want to illustrate this with one study here. This is a study, and maybe first of all, we have more than doubled our food production over the last like 40 years without increasing the area of cropland, because our agriculture gets more and more productive. So now this is a study of so-called yield gaps. So when it's dark blue, you could produce much more per hectare than people do because of inferior technology, no fertilizer, and so on. So if the whole world would produce per hectare just 50% of the potential yield, where you see like here in the UK or Germany or France, we produce at the limit, so we cannot increase yields. But if the whole world reached only 50% of the potential, you could feed 850 million more people. Here. So to cut a long story short, I mean, these projections are debated. Maybe they are too optimistic in terms of technological development in agriculture, but there are many people believing that our agricultural development could outpace the population increase. And by the way, how much resources we use, our meat consumption is much more important than how many people we are.
Thomas, I wanted to make sure that some of the audience attendees have a chance to ask questions. There is a question through the chat from Florence Jomot. Hi, Florence, by the way, who asks, you have not talked about the risk of increased prevalence of infectious disease due to higher temperatures.
Yeah.
Is that something you feel prepared to speak briefly, though?
Yeah. I mean, there are surely risks. I have seen studies on this, applying similar methods as I do in my research. But as I'm not really, fully into the literature, it's hard to say. I mean, there are definitely additional risks, and some of the tropical diseases can expand towards the north, and they're already doing this. There's a lot of data on this. But my take is that other factors are maybe more important. But yeah, it's not really my, yeah, I'm a bit on thin ice here, but it's a very active field of research. Yeah.
Thank you. And then I think I also had an email, a message from Eugenie Dugois.
Yes, thank you.
Oh, there you are.
Yes, thanks. No, you made a point that the literature on extreme events is quite advanced on the biophysical side of it, and that it seems like the connection to IAMS or economic modeling has not really been done yet. So I just wanted to hear more on this and what are the key barriers in your view there?
Yeah, well, I guess the key barriers is that normally I talk to my friends and you talk to your friends, I mean, scientifically. So it's just like, you know, communities are separated. I would guess that's the main one. And also, in terms of impact modeling, there has been a lot of development only in the last 5 years. You know, I'm, for example, working with fire models. Like until recently, we wouldn't even dare to simulate the future, you know, because the models were so bad. And now finally we start getting there. So the developments are recent, and the barriers, I think, are simply talking to each other. But you mentioned integrated assessment models. And I mean, this is a field of research where the communities come together. And, you know, some of the rather optimistic projections of future yields and the demand for land, for agriculture, I just mentioned, this comes out of integrated assessment models.
Okay, we're going to have to move very quickly on, and I was actually going to stop it here, but another question came up, which I really wanted to ask myself, so I take advantage. Tobias Ströger asks, is the increase in agricultural productivity climate impact neutral? I mean, I had the same question when you showed it. I mean, yes, we could produce much more food. Actually, I would widen the question, not just about climate impact, but also biodiversity impact.
Yeah.
If we produce much more food with much more fertilizer.
Yeah. No, this is exactly, no, this is a tricky question. I would say it's unresolved, but this will be the big challenge, you know, to make our agriculture more productive without using much more fertilizer, without using much more pesticides, without, you know, killing all the biodiversity. And this is really the big challenge. But maybe the prospects are better than we think. You know, for example, in Germany over the last 50 years, the use of fertilizer has decreased, not increased. You know, many people are very surprised about this. Actually, our farmers get more. They get beaten all the time. You know, people complain, in particular ecologists, but they have become more effective.
Okay, Thomas, we're very grateful. That was really eye-opening and very, very useful introduction to this conference. And we now move to Silvana, who will reassure us that all the actions needed are being taken to address the issues you have raised. Okay, so Silvana, on climate change actions and greenhouse gas emissions, the evidence so far.
Really not, actually, but let me share what I have. So the title of the paper is Climate Change Pledges, Actions and Progress. And this is joint work with Tiloka De-Siva from the University of Moratuwa in Sri Lanka. Now, for many decades now, countries have been debating how to reduce emissions and mitigate their impact on climate change. Those debates and negotiations have led to 3 international treaties: the Kyoto Protocol, the Copenhagen Accord, and the Paris Agreement. The pledges made by different countries in the context of these agreements differ hugely in coverage, timelines, targets, and measures adopted to implement them. In this paper, we want to study these 3 international treaties. And concretely, we want to review and better understand the pledges made by different countries, the actions taken in the form of policies and laws, and the progress made so far in terms of emission reductions. So more concretely here, we try to address 4 questions. First, what exactly were the targets in each of the agreements by different countries, and did they achieve them? Second, what was the impact of signing each of the international agreements on countries' emissions? Third, did it help to have quantifiable targets? And finally, of the actions taken so far, which measures were the most effective in terms of emission reductions? Now, to set the stage, the paper starts by documenting the trends in total and per capita emissions by country. Next, it carries out two sets of exercises. In the first set, the paper characterizes the three agreements, computes comparable targets across signatory countries, and contrasts the pledges made by different countries with the actual reductions in emissions. In the second set of exercises, the paper studies the impact of emissions stemming from signing climate change agreements, from stating quantifiable targets, and from implementing mitigating laws, policies, and specific measures like carbon taxes and emission trading schemes. So let me share a preview of the main findings. First, countries' compliance with agreements has been partial at best, with many countries vastly undershooting their targets. There's huge heterogeneity in compliance as well as in the target set. Still, signing a treaty and having quantifiable targets set in the context of Kyoto and Copenhagen has led to significant reductions in emissions when compared to the counterfactual of not signing the agreements. The effects from the Paris Agreement are not yet visible in the data. It might be too early to tell, of course. Compared to Kyoto or Copenhagen, however, the targets in Paris appear much less transparent, and we think it will be very hard to assess compliance when the time comes. Let me highlight a couple of other findings. The absolute fall in emission increases with the number of climate laws enacted by each country. Of the individual measures taken, two stand out: carbon taxes and the introduction of emission trading schemes. They are both associated with material reductions in emissions. Other climate laws or policies do not appear to have individually a significant effect on emissions. Overall, our takeaway is that it's clear that much more ambitious and transparent targets would be needed to offset the effects of emissions stemming from both population growth and GDP growth. So a lot of the effort in the paper is in the data. We built a big panel database on emissions and activity, both at the sectoral and aggregate level, for 190 countries from 1971 to 2018. Let me just highlight that the most challenging part of the analysis was actually to translate pledges made by countries in those agreements into comparable targeted emission reductions in terms of million tons of carbon dioxide equivalent. In some cases, we had to do quite a bit of detective work to compute the targets. Countries set their targets in terms of sectoral or aggregate activity. They use different years as baselines and sometimes use different units of measurement. So we needed to unify the data to make them comparable, expressing targets in terms of aggregate emission reductions relative to a common baseline year. Also, and this is mostly in the case of the Paris Agreement, some targets were stated relative to business as usual scenarios. So we needed to dig deeper in the data to find those scenarios. Sometimes they were not published in order to compute the targets. So let me give you an idea of the challenge. Pledges vary, as I said, in terms of the baseline year against which they benchmark their emission reductions. They also differ in the quantity against which they benchmark those reductions. For example, some countries targeted reductions in a sector or a set of sectors, some in terms of overall activity. And they also differ in the unit of measurement. So we use our sectoral data to construct comparable targets measured as the pledged reduction in greenhouse gas emissions from the starting year of each international pledge. Some pledges were relatively easy to quantify with available data. That's the case for most of the pledges in Kyoto and the majority of quantifiable pledges in Copenhagen. But the Paris Agreement, as I said, presented many challenges, will haunt us when we assess compliance in the future. So here, this is an illustration of some of the challenges. So an easy case of transparent target in the Paris Agreement would be Canada. Canada's pledge for 2030 is a 30% reduction in emissions relative to their 2005 levels. So to make the targets comparable across countries, we simply needed to know the greenhouse gas emissions of Canada in 2005, and then the emissions in the started year of the Paris Agreement, which was 2016. For other countries, the task was slightly more complicated. So for example, for Algeria, the pledge for 2030 stated as a 7% reduction from the business as usual scenario. So to compute a comparable target, we needed the business as usual scenario for 2030 and the actual emissions in the starting year of the pledge, again, 2016. For European countries, the Paris Agreement stated a collective EU targeted reduction of 37% below the emissions in 1990. So we needed to use separate data for the European Commission to get the numbers pledged by each individual country, which differed vastly from the average 30% in some cases. Another country with moderate difficulty was China. China pledged a 60 to 65% reduction of carbon dioxide emission per unit of GDP below the 2005 level for the projected level in 2030. So we needed a projection for 2030 as well as GDP and the emission level both in 2005 and in 2016 in order to compute a comparable target. There were examples of targets with more difficulty. For example, Trinidad and Tobago here express the reductions at the sectoral level. They committed to a 30% reduction in emissions in public transportation below the business as usual emission level in the sector. So we needed a projected business as usual emissions in the transport sector in 2030 and actual emissions in the transport sector in the started year of the pledge, 2016. So this is just to give you an idea of what's in the paper. A general takeaway from this exercise is that it would be really important in the future to have more transparent targets. That would make the task of assessing compliance and indeed of complying with the targets significantly easier.
Silvana, just a quick clarification.
Yeah.
All these examples here are from Paris.
These are for Paris, and so Kyoto was a lot easier. In fact, it was the most straightforward of the three agreements. Copenhagen, of the 100 agreements, I'll talk about that, about half have clear quantifiable targets. 10 of them, though, were expressed in terms of business as usual scenario. We had difficulty finding some of those business as usual scenarios. So I'll get to that to overstress the point, perhaps. So let me give me a few slides, and I'll get to your point. So let me now turn to the data. As you know, the level of global emissions has more than doubled over the period we're looking at here, 1970 to 2018. Global per capita emissions experienced some declines over the 80s and 90s, followed by a rapid increase from 2000 onwards. So this chart here illustrates these trends at the regional level. The plot on the left shows the levels of fossil CO2 emissions by different regions. And the plot on the right shows the levels of emissions per capita for the same regions. The biggest growth in total emissions on the left over this period, as is well known, came from East Asia, depicted in the green dash and dot line here. Though in terms of per capita emissions, countries in this group are still well below the levels in Europe and mostly North America. total emissions in Europe and North America seem to have stabilized at a high level since the 2000s. Still, on a citizen by citizen comparison, someone in North America is contributing much more than double the volume of emissions relative to someone in East Asia. Now, this is important to emphasize because if advanced countries really want to lead the way in mitigating climate change, it's important that they start by reducing their own per capita contributions in a more material way. And this issue becomes even more important if we focus on the stock of greenhouse gas emissions in the atmosphere rather than the emission flows. The paper goes in more detail into the top emitters, so I will skip this in the interest of time. But needless to say, a big part of the problem are also oil producers. In per capita terms, the top emitters remain rich countries and/or oil producers like the US, Canada, South Korea, Japan, Germany, Saudi Arabia, and the like. And these observations are confirmed by simple regressions. GDP per capita and population have been the key drivers of emissions, as shown in this table. Roughly a 1 percentage point increase in GDP per capita translating to 0.80 basis point increase in emissions. And population growth moves growth in emissions more than 1 for 1. Oil production, as I said, also is a big determinant of emissions. As you can see here, the effect gets absorbed in the country fixed effect in the last column. Now, let me show you a rough summary of the 3 international agreements. So the Kyoto Protocol was signed by 37 countries, contributing to about 1/5 of global emissions. Our starting year to compute Kyoto targets is 2005. All the 37 countries gave numerical reduction targets, but for 7 of those countries, we were unable to reconstruct the numbers. So for these other 7 countries, we're still searching. For now, we will count them as countries with no quantifiable goal. There's certainly no easily publicly available information to compute them. When we computed the targeted reduction with respect to 2005, it turns out that this group would have seen an increase in emissions in the order of 7% from 2005 to 2012. The increase is mostly due to the inclusion of Russia here. If we exclude Russia, the joint pledged reduction is in the order of 5% over those 7 years. Needless to say, this is not enough to offset or compensate for the pace of global growth during those years. Copenhagen was more ambitious in terms of coverage. 100 countries signed it. Of these 100 countries, 59 stated numerical targets, 5 of which couldn't be reconstructed because there was not enough publicly available information. So in all, 54 countries had clear quantifiable targets amounting to an overall targeted emission reduction of 4% over the 11 years. For countries with non-quantifiable countries, so the other 40% here or 50%, we cannot really compute targets or assess compliance. Non-quantifiable targets include 2 types of pledges. The first type are the pledges where there is a percentage reduction stated, but there isn't enough publicly available information to compute how the pledge translates into tons of carbon dioxide equivalent. So for example, they use a business as usual scenario as a baseline, but we don't have the data on the business as usual projections. The second type is where the countries do not mention a specific percent or quantitative reduction, but something vaguer. For example, they pledge to adopt nationally appropriate mitigation actions to reduce emissions, but without providing further details. So this is important for the Copenhagen Accord, for which many countries did not give quantifiable targets. And finally, turning to Paris, again, this was more ambitious, at least in appearance. covering 188 signatories. 149 had a numerical target, but only 117 had quantifiable targets. For those, the targeted reduction in emissions amounted to 7% over the 14 years of the pledge. I should add here that there's huge heterogeneity, and I'll show it to you later, around these mean or aggregate reductions. And I'll come back to this point. So let me now turn to the comparison of targets and achievements, starting with the Kyoto Protocol. This chart portrays actual reductions in emissions in the vertical axis against targeted reductions in the horizontal axis. A positive number here is a reduction in emissions, and a negative is an increase in emissions. Now, in the next chart, I will exclude Sweden and Ukraine, which are big outliers here, with a target for increases in emissions rather than reductions. But just before I exclude them, let me explain why Sweden looks so odd. Sweden falls under the European Union umbrella. And even though as a whole, the European Union targeted a reduction of 8% in the Kyoto Protocol, the individual country pledges show that Sweden was allowed a 4% increase in emissions from its 1990 emission levels. In 1990, Sweden's greenhouse gas emissions were around 47 million tons of carbon dioxide equivalent. So that means that their target for 2012, allowing for that 4% increase, would have been 50 million tons of CO2 equivalent. Now, when we compute the comparable targets, we measure the targeted reduction or increase from the start year of the pledge, which was 2005. By 2005, Sweden's emissions were already quite low, around 12 million tons of CO2 equivalent. So then if they are targeting 50 metric tons of CO2, starting from 12, then the resulting target is clearly a huge increase in emission. So all to say that for Sweden, Kyoto was not a particularly demanding pledge. They were already there. And as were many other countries, really, just with different magnitudes. So let me get to
Silvana, just understand this. So a negative number is an increase in emissions in this picture.
That's correct.
Okay.
Yeah. So let me go over this again. So countries to the right of the y-axis, of the vertical axis here, in shaded gray, had targeted a decrease in emissions. Countries to the left of the zero axis had targeted an increase in emissions, or relative to the levels of emissions in 2005. Countries above the x-axis here are the ones that actually experienced a reduction in emissions, and countries below the horizontal axis recorded an increase in emissions. Countries above the 45-degree line are the ones who achieved or exceeded their target. And obviously the task of achieving the target should be easier the more to the west of the picture the country is. Now, the shaded cone here, the dark gray cone, highlights the countries that both pledged a reduction in emissions and achieved their pledge. And it's really a small minority, showing that not only the targets in the Kyoto Protocol were in all rather unambitious, but also few countries actually complied, few countries committing to reductions. Let me now turn to the Copenhagen Accord. This is the same chart as before, but for Copenhagen. And again, I will exclude 3 outliers here: Latvia, Serbia, and Antigua and Barbuda, to see the picture in a better scale. Remember, as before, the horizontal axis shows targeted reductions in emissions. The vertical axis shows actual reductions. What's interesting in Copenhagen is that if you look at the cone of compliance with targeted reductions, there are really very few countries. Of the set of compliance above the 45-degree line, most had pledged no reductions in emissions or increases in emissions. There are still 2 more years to go because our data ends in 2018 and Copenhagen runs until 2020. And certainly the pandemic would have helped many of these countries to reduce emissions, but that would have led to compliance by accident rather than by commitment. The overall takeaway is unchanged. It would have helped to have more compliance and let alone more ambitious targets or pledges. And let me now turn to Paris. We can only observe the pledges at this stage as it is too early to assess progress. Because a lot of the pledges in Paris are very opaque or expressed in terms of scenario projections, in the fullness of time, we think it will be much more difficult to assess compliance than for Kyoto or Copenhagen. In any case, Paris targets are for 2030, so we cannot discuss compliance yet. This plot is different from the other two. It shows the targeted emission reduction in the vertical axis against the level of emissions in 2014 on the horizontal axis. There are still many countries in negative territory here, implying that for them, the Paris Accord means a targeted increase in emissions. So these are all the countries below the 0 line here. The other point to highlight is that the heterogeneity or range of pledges is huge in Paris. Sweden, for example, here is pledging a reduction of more than 80% in emissions relative to their levels in 2014. And there are other countries along with Sweden, like Namibia, Romania, also pledging large reductions. And in contrast, there are many other countries that are targeting very large increases in emissions. So as I said before, the targeted reduction from Paris overall, so the average from all these numbers, based on the elements we had to compute those targets, was in the order of 7% relative to 2014. So let me now turn to a second exercise that does not involve the computation of targets. It instead tries to look directly at the impact of the agreements on emissions. More concretely, this table here shows the regressions obtained, or regression coefficients obtained from regressing the level of emissions in logs on dummy variables that take the value 1 if the country signed a particular agreement and 0 otherwise. And we have 1 dummy for each of the agreements. It also controls for GDP per capita and population, as well as for country and time fixed effects. So the first column, for example, tells us that signing the Kyoto Protocol led roughly to a 30% reduction in emissions in signatory countries when compared to the countries that did not sign it. So just to put this number that appears large together with the other small number that I showed you before, let me highlight that this estimate is like a diff and diff, as we are controlling for country and year fixed effects. So I showed you before that countries signing the Kyoto Protocol were targeting an average reduction of around 5% when excluding Russia. Including Russia and taking into account the lower compliance, the actual reduction would have been much less. But the control group here in this regression is the countries that did not sign the Kyoto Protocol and saw significant increases in emissions. So in other words, the 30% effect here is coming from the comparison with the control group that saw massive increases in emissions. So while Kyoto did not lead to a large net reduction, it put the lead on more increases for signatory countries. Signing Copenhagen, all else equal, again led to a reduction in emissions in the order of 15%, again compared to the group of countries that did not sign it. And Paris has not yet produced any reduction in emissions. The second column here includes a dummy variable that takes a value 1 when the country has a quantifiable target in the agreements. And having a measurable target was important for the fall in emissions, and we find a significant effect coming from that. So bottom line, numerical targets help, and we should say by transitivity, having clear, transparent targets should be helpful.
Can I ask you a quick question on that slide?
Yeah.
Did you run this regression with the actual target as a right SI variable?
No. No. We can certainly do that. We wanted to distance ourselves from the target measures, but yeah, we can definitely put them. Yeah, definitely. Okay, so the next exercise we do in the paper is to study the climate laws and policies passed over time by different countries. The number of actions has increased significantly, particularly since 2000, both in the form of laws and policies. So in these regressions, we zoom in on a couple of those policies that actually ended up being quite significant: carbon taxes and emission trading schemes. Both appear to have a significant impact on emissions. Having a national level carbon tax appears to reduce emission by 16%. Having an emission trading scheme has also a material effect, slightly smaller than carbon tax, but still material. Other specific policies do not have a material effect, at least not individually, but the overall number of climate-related laws passed in a country does appear to reduce emissions. Now, many of these measures were taken with the goal of complying with the targets in international agreements, and so to an extent, it's not surprising that when we include them, the effect on the international agreements decreases a bit quantitatively. They're still significant, both economically and statistically. Now, the regressions so far provide some suggested evidence that on the emission impact of international agreements and the specific actions. But one might question causal inference from these estimates because they can be affected by feedback effects from emission levels to climate change actions or to the willingness to sign the international agreements. So for instance, a country with a low level of emissions may find it easier to sign a climate agreement than a country with a high level of emissions. Or in the other direction, a country with high level of emissions might face more international peer pressure to join the agreement. So to address this problem, we also estimated the dynamic effect of climate change actions using the local projection method of Jordan. And the key identifying assumption here is that once historical emissions and other covariates are controlled for, we are left with the unexpected or the exogenous component attributable to the policy. So let me show you what we obtained from doing this exercise. Oops, sorry. Here. So these 4 plots show the impulse responses of emissions to 4 policy changes: signing the Kyoto Protocol, top left; signing Copenhagen, top right; having national level carbon taxes, bottom left; and introducing an emission trading scheme in the bottom right. So what we find is that the effect on emissions from each of the 4 interventions builds up gradually over time. By the 4th and 5th year, the estimated dynamic effects are broadly similar to the results I showed you previously in the regressions, with the 4 policies demonstrated significant and persistent negative effects on emissions. Now, as before, these numbers should be interpreted relative to the counterfactual provided by countries that did not put in place similar measures or similar interventions. So to the extent that countries in that control group recorded significant increases in emissions, the actual reduction in global emissions is, of course, much more modest. So let me now turn to our conclusions. Going back to the initial questions, climate targets were not always clearly specified, and this is a problem that will become even more important for the ongoing Paris Agreement. Our first observation is that it would be very helpful to have more transparent goals. Countries' compliance with those targets has been partial at best, with many countries undershooting their targets. Still, signing the Kyoto Protocol and the Copenhagen Accord has led to significant reductions in emissions when compared to the counterfactual of not signing the agreements. The effects of the Paris Agreement are not yet visible in the data. We also find that having quantifiable targets in the context of Kyoto or Copenhagen helped further in reducing emissions. We find that the absolute fall in emissions tend to increase with the number of climate laws enacted by countries. And of the policies we looked at, two stand out as important, having national level carbon taxes and introducing an emission trading schemes. They are both associated with material reductions in emissions. Other climate laws or policies do not appear to have a significant impact. Finally, while signing the agreements did help reduce emissions in comparison with a counterfactual, the reductions themselves were rather modest. And much of the significance, as I said, stems from the fact that the control groups increased their emissions in a massive way. So overall, our conclusion is that much more ambitious targets would be needed in order to offset the much bigger effects on emissions stemming from GDP and population growth. I'll stop here.
Great, Silvana, thank you very much. So while you were speaking, there was a discussion in the chat, which I want to bring you in and get your views on leakage and shifting of emissions across countries. So, to make this perhaps even more pointed about your regressions, to what extent should we worry that the effect you pick up in your difference in difference is driven by signatory countries shifting their emissions to non-signatory countries?
I mean, that's a possibility. So they're suggesting that this would be underestimates of the effect. Is that?
I think, well, you can think of, I think the concern is that it's an overestimate in the sense that basically the world is, one interpretation of this concern, as I read it, is that the world has emitted as much as it would have without these treaties. Only the geographical distribution of these emissions has changed away from signatory countries to non-signatory countries. I mean, I'm reading it in a very extreme way, I think, the discussion.
Yeah. Look, I mean, that's certainly a possibility, and there's nothing we can do about those spillovers. It is.
Are there provisions in these treaties that limit countries' ability to do that?
I don't think so. Yeah, but yeah, I mean, it's a good question. There's nothing we as from the econometric side could do about that. I mean, we cannot control for those leakages, or unless we have other sources of information that report on that, there's nothing we could do. Yeah.
I mean, I was surprised you found out any effects from the Kyoto Protocol at all, because it was only about 5 years effective. and then it collapsed. I mean, America first left, and then it kind of quickly unraveled, and so the emission limits were only about five years. So maybe these signing these protocols is something else apart from the agreements. It's interesting, your results. They're small, but they're even bigger than I would have thought.
Yeah, I mean, clearly, once we introduce specific policies and carbon taxes and in particular and emission trading schemes, those take away from the actual signing. So in some sense, to the extent that they were part of the agreement, they will be collected in these other terms. We were surprised to find effects, as you know, especially when you look at the targets. They were so modest, and in fact, Kyoto was targeting an increase in emissions once you take into account Russia. But I guess the you know, as I said, to some extent, it was so much worse not to sign, or what countries that didn't sign did, that in the end, Kyoto did have an effect, at least in putting a lead in the growth of emissions, putting some caps. So in some ways, it's a mixed result. Kyoto did help, but just because the others were doing a lot more in terms of emissions.
May I ask a question?
Yeah, go ahead, Lint.
Have you thought of, or have you looked at corporate pledges and what role they play, or whether those translate into emissions reduction? So Facebook, Google, Amazon, so many companies are now also making emissions reductions pledges. Have you thought of extending your analysis to look at those?
We haven't done that, but Tarun Ramadorai has an exercise that will go in that direction. I don't think they have the big corporates. They have, I think they look at a set of companies in the US, and they find that having targets does help in reducing emissions. So that would be a micro counterpart to this for US companies. So they are pushing that idea. Again, I can't compare exactly the magnitudes, but there was something there. And it would be interesting to look at, you know, eventually at Facebook or, at the big corporates. I mean, my sense is that, it's more what the consume is. It would be interesting to look at what consumers of Facebook produce in terms of emissions, not just what Facebook as a company in headquarters produces, the whole services. That would be really an interesting exercise.
If I may jump in, I just wanted to share two sort of thoughts. One is that the targets are sort of endogenous here, and in a sense, they're signing these agreements because they're fine with these targets. So increasing the targets may not do anything else but actually preventing an agreement in a way. Like, it's not clear, right, that we can't force countries to increase the targets, because that's kind of the issue of the global public good here, and having no legal jurisdiction to force countries to do anything. So it's and the second thought is I just wanted to say one word about the technological change that's happening in the background. And so even though you have country fixed effect and year fixed effect, you're going to have some country in time variant aspects related to technology, in particular in the energy sector. In the 2000s or so, like, we get emission reduction from energy efficiency improvements that are rational to do in a way. Developed industrialized countries had clear incentives to do that, and also like a phase out of coal for cleaner natural gas. And so I think like the effect that you're capturing has that, like the effect of maybe signing, the effect of collective action. Like I completely believe that, but I guess there is also some background changes in technology that are not specific to Kyoto?
Yes, so I mean, the first point on causality, we're painfully aware of that. That's why we try to do the local projection models where we control for emissions. And one thing we haven't done yet, but we want to do, is to use propensity scores and local projection models. So in that case, we can control, at least for selection in observables. So compare two countries that are very, very similar in terms of the propensity to sign the agreement, and then look at reduction in emissions and vis-a-vis those. So that's in the making. Hopefully we'll
Can I add one thing on that point? I mean, maybe you can use some politics instrument. You know, did they have a right-wing government or a left-wing government when the treaty was signed? I mean, things like that might give you some exogenous variation in whether they were willing to sign or how aggressive they wanted to be in the signing.
Yeah, that's a great idea, Francesco. We can try to look for that info and get an IV. Yeah, that's a great idea actually, because with the propensity score we can only control for selection in observables, but if there are other unobservables, we would need a better instrument. Yeah.
I had one question, which is
sorry, Larry. I have Elizabeth Baldwin that has been waiting to talk. So if you don't mind, I will let her come in. Do you want to come in, Elizabeth? I think I have just.
Sorry, my question was perhaps a bit similar to the discussion we just had, but I saw that there was a similar size effect from signing Kyoto and from having carbon pricing. And so kind of following on from what Rick was saying, can we, because these are typically going to be the same countries, can we disentangle a real effect of Kyoto there? Or is it that the countries who decided for their own reasons that they were going to cut emissions a bit, did it via carbon pricing, and by the way, they signed Kyoto on the way? So if we can look at the countries that aren't actually in that overlap and look at the effects on those countries that only did one or only did the other, is it possible to disentangle those a bit?
Yeah, I mean, in a way, that's what the regression exercise tries to get at. You know, you look at the effects of the two separately, and what we find is that they both matter. So it's not that the introduction of carbon taxes completely killed Kyoto. Kyoto has still a significant effect over and above those carbon taxes and over and above the emission trading schemes. So that's what the exercise is trying to capture.
Hey, Larry?
And Larry.
Yeah, my question is about the timing of these targets. You know, there's a kind of a goal being set into the future, and I'm just wondering about the green, the green paradox issue, whether that could have, undone a lot of the good that these agreements have done. But, delaying, telling the producers of dirty energy that it's lose it or use it or lose it, and that leading them to accelerate their burning of fossil fuels. That's my question. I don't know whether you have any feeling for whether or not these things were phased in too slowly, because we're probably going to have another agreement at some point, and we could probably use some direction on that.
Yeah, look, it hasn't jumped up in this exercise we have done. I think it's a serious concern, and again, it might be something to watch in Paris. It's an extremely serious issue. I don't think there's a way to. We can zoom in on oil producers here and see if we saw an acceleration there in Copenhagen. Yeah, we'll think more about it. I think it is a risk. Yeah, I mean, but it's particularly a risk, I guess, with Paris because most countries have signed it. Yeah, we'll think about it and how to get that.